doing? So I guess while we're kind of waiting a little bit for people to shuffle in, does anybody have any questions about any of the stuff we talked about last time? Course stuff, life in general, anything? If anybody has anything, now would be a good time.
Professor, I had a question.
Sure.
So will we be dealing with nonlinear control as well?
We are mostly dealing with nonlinear control. Yeah, almost. Yeah, that's like the meat. Yeah, it's all the nonlinear good stuff is what we're going to talk about.
Great.
The linear stuff is because like it's the stuff we know how to solve, and almost everything in nonlinear control is like based on sort of bootstrapping from linear stuff and like trying to iteratively, approximate based on linearizations and things like this. So yeah, there's like, I guess, deep insights to be gained from the linear stuff, and also practical algorithms that are based on like the inner loop of a lot of the algorithms is linear, as with all things, I think, in computers, right? Like we know how to solve linear equations, we know how to do matrix math. So that's what those are the tools we have, and we try to make the best of them. I think that's kind of the deal. Yeah, anybody else?
Anything in manipulation? Do you have any problems that relates to, say, dynamic manipulation?
I don't know that we're going to have, so that's not what I do in my particular, like in my research. That said, the tools are definitely applicable. And if that's your primary area of interest, like I would love to have you like work on a project that's manipulation focused. I think that would be, yeah, totally fair game and definitely doable. And I think there's a lot of cool things. We can definitely work in like some examples and some homework problems, like on a 7-DOF arm, for example. That's very doable. Yeah, so there's no reason not to do manipulation, I suppose. It's just it's not my wheelhouse, so I'm like less likely to draw from. I'm more likely to draw from like manipulation of locomotion and like aerospace examples, just because it's my background. But yeah, it's totally applicable and would be great to have. We'd love to have you and like love to have you work on some a manipulation project.
Perfect. Thank you.
Cool. So yeah, anybody else? I'm gonna like get my tablet queued up here.
Yeah, last time you said that if we add damping, then we will get strictly negative eigenvalues.
Yeah.
But there will still be some oscillations.
There will still be oscillations, but the real parts will be negative.
Yeah.
Okay. Yeah. That's what I meant.
Okay.
Yeah. No, it's still normal physics and everything applies. Yeah. What I meant by that is it's strictly stable in the sense that the real parts of the eigenvalues are strictly negative, not zero, right?
Good.
Cool. Joining. And if I made any mistakes in the notes, definitely let me know. We're getting, so I have my PDF ones that I put up, and also we're gonna be, Tanmay, one of the TAs, is graciously agreed to scribe my scribbles into LaTeX. So for all of your reading pleasure, so that you don't have to read my horrendous handwriting. So hopefully that helps. And so yeah, along those lines, like we'll be posting those PDFs soon, and definitely like it's the first time running through this, and like I make mistakes. So if you catch stuff, definitely speak up and tell me, like preferably during lecture. Yeah, feel free to just speak up in lecture, and then also if you catch stuff afterwards that's mistakes or unclear or whatever, definitely let me know, and we can try to fix stuff as best we can. All right, I think this is working. Share screen. Okay, the iPad is live. Hooray! Everyone see that? All right, good deal. So yeah, if there's like also, if anyone has suggestions on how to do this better, I'm all ears too. Okay, cool. So just a quick recap from last time. Last time, in addition to the intro material, we talked about dynamical systems, controlled dynamical systems in continuous time, right? And And what did we do? We talked about manipulator dynamics. Those are important. We talked about equilibria for these kind of systems and the fact that you can kind of engineer them with control in fun ways. By the way, that's a sort of quite nonlinear thing. And it's sort of almost inherently nonlinear. The fact that you can like erase and create equilibrium points and bifurcations, that's a very, very nonlinear territory. And I'll have some references for these things too that get into the PDF notes if you're curious about more of this kind of stuff. And then the last thing we talked about was stability ideas. And specifically, we talked about local stability, this linear stuff. We also talked about basins of attraction, which is a more global notion of stability, but kind of only in that 1D case. Okay, cool. So that's like last time what we did. Today, what we're going to do is start heading more into computational land with this stuff. So we're going to really talk mostly about making this continuous to discrete transition. So like how to go from continuous ODEs to discrete time simulations that you would implement in software and that we'll actually end up using in our algorithms, right, for the most part, and a little bit more about stability and how that kind of looks in this discrete time setting and some of the fun additional things you have to worry about when you start discretizing things. Cool. So just as a quick motivational sort of aside on why we're talking about this stuff, as I'm sure most of you are aware, now that you're sort of, far enough along in your engineering lives, in general, we can't solve these equations, right? So they are of limited use to us, right? Even if we have this nice ODE model, we can't get X of t. So that's annoying. So we need ways of simulating things. Also, we need tools for control design, right? If we can't solve the ODEs, we also can't in general design good controllers using those things. So and also, in a computer, inevitably we need to go from discrete. We need discrete quantities, finite dimensional things. So like X of t is a continuous function, and we can't really represent that in a computer other than as a set of discrete points, right? And also there's some other sort of interesting things about that. So like in some sense, discrete maps, these discrete time dynamics we're going to talk about, in a couple of senses, they're actually more general than the continuous time ODEs. There are actually dynamical effects that we can capture with discrete time models that we can't capture with continuous ODEs. And that has to do with the fact that the ODEs have to be smooth. Just by definition, they're smooth functions, right? So there are functions, there's things that happen in dynamics that are non-smooth, namely impacts, friction, et cetera. And those things can't be written down as ODEs, period, end of story. So like, but they can be posed as discrete time maps. And so there are things where the discrete time stuff is like more valuable and more general than continuous time stuff. All right, cool. So that's it for that commentary and what we're up to. All right, so let's get into it. So first off, like generic discrete time dynamical systems. So first we're going to talk about what I would call the explicit form of these things. So that's where you have a function that takes in the current state at time k and the current control at time k, and spits out the state at the next discrete time step k plus 1. And we'll, for now, just because we're gonna like have to write down both continuous and discrete versions in the same lecture, I'm gonna put a little subscript D for discrete on these guys to distinguish them from the continuous version without the D. And probably I will drop this later and sort of overload notation and trust that it's clear from the context. Okay, so that's pretty easy. And probably everyone's seen before this like simplest version of this. Which is the classic, albeit somewhat terrible, forward Euler integration. So this looks like xk plus 1 equals xk plus some time step h times your continuous dynamics. And for now, I'm going to like leave off the, actually, I'll put it on for this one. I'll leave the u's in there. Okay, so this is forward Euler integration. This is a time step. And I'm assuming like pretty much everyone has seen this before. If not, let me know. So we'll go a little fast on this stuff. Okay, so that's super simple. What we're gonna do next is we're gonna take this thing, and I have to switch gears now. We're gonna try this out on the pendulum from last time. So, screen sharing fun. Let me stop sharing this one. Cool. Okay. Can you guys see this?
Yeah.
Yeah, awesome. Okay, so Jupyter Notebook, Julia, for those who've never seen it before, not too terrible. Jupyter Notebook still exists for all you Python folks. So here's my pendulum dynamics with like m equals L equals 1 that we talked about last time. Super easy, right? And then here in this function, I've written down exactly what we just wrote down, right? So xk plus 1 equals xk plus time step h times f of x, right? Okay, so there we go. I'm going to simulate this from like an initial condition pretty close to the downward equilibrium. So initial velocity 0 and initial angle 0.1 radians. So just like nudged over a tiny bit. That's the x naught. We're going to run this for like 5 seconds with a time step of 0.1 seconds. Seem reasonable? So 10 hertz, 5 seconds. Let's see what happens. So we start out with our little oscillation there, and it looks like it's blowing up on us. And if I like carry this out a little bit farther, let's say I go to 10 seconds, it really blows up. If I shrink the time step, maybe I think, oh, 0.1 seconds too big. Let's go to like, I don't know, we can do 100 hertz if you want. It's still blowing up. So it means like I can take tinier time steps. It'll take longer to blow up, but it's still blowing up. Okay, so now the question is, what is going on here? So I'm going to switch back to the tablet now. The switching is very awkward. Makes me feel like I don't know how to use my computer. Okay, so that's awkward. What happened? So I'll just put a little place. We'll try to like stuff that in the PDF somehow, I guess. But I'll like, I'll just throw in here. L equals m equals 1. H equals n at 0.1. We also did 0.01, blah, blah, blah. But blows up, right? What's going on? So in order to answer the why part of this question, we now get to talk about stability of discrete time systems. So That's whatever. So I guess this deserves a section break. Okay, so in continuous time, what do we have for our stability condition? Had this thing that was like the real parts of the eigenvalues of the Jacobian had to be strictly negative to be stable. So let's look at the discrete time case. It's I don't have as pretty a picture for this one as last time for that 1D case. I really like that like little 1D example, but there's like a fairly intuitive way to get at this in discrete time too. So in discrete time, we can think of the dynamics like a simulation, like I just ran for you guys. We can think of that as an iterated map. So I'll show you that, what I mean by that exactly. So like if I want to simulate, you know, n time steps up to time step n, I'm going to get like f of dot, 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 f of x naught, right? So I'm applying the function f like n times to get myself to time step n, right? Cool. So everyone good with that? So now if I linearize this thing, what's going to happen? So if I just like chain roll this thing, right? Like the obvious thing is going to happen. So what I'm going to try to do right now is I want like dxn dx naught, right? I want the Jacobian of the whole iterated map, right? And that's going to be just like partial f, partial x, you know, the first one, blah, 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 chained all the way down like this, right? So I'm just multiplying those Jacobians.
Exactly.
Yeah.
The F here is actually the FD.
Oh, sorry. Yes, you were right. I already slacked off on my notation. Good catch. Thank you. Correct. This is the FD. Right. Okay. So that's what happens. And we're going to abbreviate this guy as is standard in linear systems control, et cetera, as A. So I'm going to start writing A's, and we'll call this one AD for discrete time A, just to be extra careful. So this is basically what I got here, right? Is if I assume I'm like, you know, really close to the equilibrium point, I'm linearizing about the x naught is like near the equilibrium, whatever, then this A stays kind of the same, and it's just A to the n, right, for n time steps. So then let's like, you know, simplify our lives and assume that the equilibrium point is the origin, which we can always do by just like using a change of coordinates. So assuming that, assuming we chose nice coordinates, then what we're going to find is stability of this thing implies that if I take the limit of this iterated map thing, so what I want here is like limit as k goes to infinity of a to the k, discrete A, right, times x naught. This has to go to 0 for all x naughts, right? That's what stable means. It means if I pick any little x naught in the neighborhood and I like iterate this map forever, stability means it's going to converge to the equilibrium point, to the origin, right? Okay, so if that has to be true for any x naught, that means it basically that the matrix A to the k, like a to the infinity has to go to 0, right? So it means really I can, for all x naught, means I can basically pull the x naught out. And it means that this limit this guy has to go to 0, right? So my matrix has to go to 0. Okay, so now what does that tell me about the eigenvalues of AD itself? So that tells me something about, well, yeah, it obviously says something about these eigenvalues. So I want to infer something about this thing based on this condition.
Less than 1.
Less than 1, that's right. So it means specifically the modulus, complex modulus of them. So if they're complex, whatever, they all have to be less than 1, right? So as I multiply them by each other over and over and over again, if they're at all less than 1, then that infinite sort of product is going to get driven to 0, right? So if all the eigenvalues have modulus less than 1, norm less than 1, if I take like an infinite product of them, eventually they're going to get driven to 0. So that means all initial states are going to go to 0. So another way of stating this, and like the way you've maybe heard it before, is that all of the eigenvalues have to be inside the unit circle in the complex plane. Okay, so I'm guessing most people have seen this step before. Anybody have any questions about this? All good? All right, cool. So let's try doing that to the pendulum with our forward Euler integration. Okay, so we have xk plus 1 equals xk plus h times f of xk for our like uncontrolled system. This guy is our FD. And so what we're going to try to do here is come up with AD. And we're going to do this about the lower equilibrium point, right? Is partial FD partial x. And I can just do this by eyeballing this guy, right? So this is going to be partial xk. It's going to be I from the xk term here. And then plus just h times like the continuous time A matrix, right? And we worked that continuous time A matrix out last time. I'm just going to write it in here. So it's like, looks like this. So let's see. So what I want to do now is evaluate the eigenvalues of this guy using the parameters we just used for our simulation, right? So if I plug in, so I want to evaluate this thing at, let's say, what do we do? Theta equals 0 and like everything 1 basically, right? So if I do this, I'm gonna get 1 plus or minus 0.313, some other stuff, I. So is that thing in the unit circle? Most definitely not, right? So unstable. So let's look at some, now I will switch back awkwardly to my Jupyter notebook. This definitely needs to be improved. Switching is awkward. Okay, so this was what we did. Okay, so what I'm gonna do now is here's my discrete A matrix. If I wrote a little function to implement that guy, like we just wrote down, I can evaluate the eigenvalues of it. I'm going to do it at 0.1 seconds, like our first simulation here where it blew up pretty drastically. So let's do that. There's that number that I wrote down on the notes, so I didn't lie to you. That's what it is. Okay, so you could say here, you know, okay, that seems bad. Maybe 0.1 seconds is too big of a time step. So maybe I want to make it smaller, blah, blah, blah. We kind of did that last time where we went up to 100 Hertz instead of 10 Hertz. And yeah, that looks better, but it's still blowing up. So let's see what this, so what I'm going to do here is I'm going to evaluate these eigenvalues for a whole bunch of possible time steps from h equals 0 up to, I guess I went up to h equals 0.1 because we already know 0.1 is unstable. And I'm going to plot this. So here's what happens. And I'm plotting, by the way, yeah, like the complex modulus of these things, right? So what you find is that, and you can kind of see it from looking at the matrix too. This thing's only marginally stable, not blowing up inside the unit circle, et cetera, in the limit as h goes to 0. So if you have any finite time step with this forward Euler integration, it's gonna blow up. It's gonna be unstable. It's like provably unstable from this simple like argument we just made about the eigenvalues, right? That's kind of weird. Does anyone have any thoughts on this? You've seen this before? Okay. Now I have to switch back.
Isn't it because we're assuming it's ideal?
Say that again?
Isn't it because we're assuming it's ideal? There's no
What?
friction, there's no loss, there's no damping.
Not really. So like what happened here is like we took a system that was okay, technically marginally stable, right? But has bounded oscillations, right? Is not blowing up. I discretized it and simulated it with this integrator, and it blows up in the simulator. So like there's energy being added to the simulation artificially from the integrator that's not in the physics. Come on, iPad, you can do it. So there's something weird going on here that's unphysical, right? Like there's nothing, it happens for any time step. Like what happened here is like, I can make the time steps as small as I want. You know, I can take 10 kilohertz time steps and it's just a matter of time. It's gonna blow up. All I can do by taking smaller and smaller time steps is like stave that off for a while. It's always gonna blow up. So it has not, it's like purely like, it's a weird artifact of Euler integration. Basically like, so I'm just gonna like make some notes here about what we did, and then we'll dump this in later.
Hi, Zach. Can you just clarify what you mean by blow up?
Yeah, so I mean that it's unstable. Like if I take the system that's supposed to oscillate, you know, nice. Like if I have a perfect ideal pendulum and I just like do this to it and let it go, it's going to swing back and forth like that with like the same amplitude forever, right? In like an ideal setting, right?
Right.
So what happened here is instead of that, I do the exact same thing, same initial conditions. And what's happening in this simulation is that the amplitude's growing, and eventually just goes nuts and starts like whipping around like crazy. So that's what I mean by blow up. Does that make sense?
Yes.
Okay. So yeah, that's not supposed to happen, right? Okay. So yeah, the cartoon thing is hopefully clear. So this thing is only becomes, you know, basically for any time step, this is bad. This simulation will give you garbage, basically, for any finite time step. Okay, so I want to just kind of, yeah, we'll kind of like make some commentary on this, I guess. So there's a takeaway message in here that I wanted to share with all of you because I've seen lots of people use Euler integration, and you know, you should. So number one is discretization, i.e. like using an ODE integrator, is never perfect. And it can in fact qualitatively change the behavior of the dynamics from the discretization. Like weird things can happen, right? So like basically you always want to be careful. And like sanity check what comes out. So yeah.
Hey, Zach. So
yeah.
the intuition here is that during that small time period h, your acceleration is actually smaller than fxn or smaller, but now you're adding hfxn, you're assuming during that period of time acceleration is always fxn. Is that the problem?
That's kind of right. Yeah, so that you're getting at it. There's actually a kind of a nice picture for this. What's happening is you're kind of overestimating the magnitude of the acceleration all the time with this approximation. Let me draw you a picture. Yeah, that's like very much what you're saying, right? So imagine like I have my sinusoid as what the solution should be, right? So let me draw a sinusoid real quick, and then let's look what's happening. So like if I'm here and evaluate the dynamics here, I'm getting like the tangent to this curve, right? If I take a step in that tangent direction, I'm going to overshoot, right? And now if I like, let's say I'm down here, same thing's going to happen down here. If I'm like here and I evaluate f here, I'm going to overshoot the sinusoid, right? So you end up with this like overshooting behavior that just kind of compounds, and it's like impossible to not do this with naive Euler integration. Essentially, you're always going to overshoot. You're always going to get this kind of bad energy behavior, and you're going to get blowups. So, yeah.
Yeah, that makes a lot of sense.
Okay, so yeah, things you should always keep in mind, right? Be careful when you discretize. Always sanity check your simulations. Good things to check when you sanity check are energy behavior. So like plot the total energy of the system. If it's like a really good benchmark thing to do when you're trying stuff out is put in a conservative system that should conserve energy, simulate it, plot the energy over time, make sure it's not going nuts. If you have a system with damping, plot the energy, make sure it's going down, make sure you're actually getting energy dissipation, right? Stuff like that. What else do we have to say? And then like the big takeaway thing, which just down here, is really honestly you should not be using forward Euler. It's the easy thing to code up, but it's sort of terrible. So if you've been doing this, you should probably not do it anymore if you can help it.
This is universally true for any dynamical system.
I'm going to go ahead and say you should never use forward Euler integration. Yeah, because doing better is it's very easy to do better. Basically, you can do much, much better for like 2 extra lines of code, which is what I'm going to show you next. So like, just don't do this, basically. It's really never a good idea, and it's almost never worth it in practice. You can get away with it. So if you have a system that's heavily damped naturally, like if the real physics have heavy amounts of damping in them, then this will work and won't blow up because the natural damping of the system is enough to counter the energy sort of inflation behavior of the integrator. But there's basically just better things to do, that you can do that you don't have to worry about this with. Okay, so let's talk about better things to do. So we're going to talk about a couple different better things to do. First thing is, and hopefully everyone who's done any of this before, seen this before. The fourth order Runge-Kutta method, which is the classic sort of industry standard method, right, that everyone uses. So really quick, just overview of what that looks like. And some fun plots like the ones we just did. This is sort of the, yeah, like I said, the workhorse. Okay, so the intuition for this, I'm not going to derive this. I think probably everyone's at least seen this before or used it before. Basically, what's going on here is Euler integration. It's assuming the trajectory is piecewise linear and fitting lines over each trajectory segment. And rather than just fitting a line, RK4 basically fits a cubic polynomial. So like it's fitting little splines over each step. So this quite obviously gets you much better accuracy. All right, so, and just, yeah, you can get this on Wikipedia, so. We'll do this just because, but if you have questions about this, I'm happy to go into like more depth on any of it. But the basic gist of this is we need to do 4 function evaluations instead of just 1. So we evaluate the dynamics at the initial step, then we do a bunch of like in the middle kind of evaluations. So we evaluate at like the midpoint, a different flavor of the midpoint. And then at the end. And at the end of this, we like basically take the step as a weighted average of the different evaluations. So the middle ones get weighted heavier. That's the recipe. And this, yeah, like I said, this has been around forever, and like tons of stuff uses this. Okay, so what I want to do now is I want to like go revisit those pendulum simulations. So that means I have to do the awkward switch again. So if anyone has any questions while I awkwardly switch, please.
Professor, I have a question.
Yeah.
So previously you mentioned this overshoot is this overshoot is caused by instability of the system, but it seems like this is caused by some numerical issues. So I'm kind of confused. Like, what's the root cause of this?
The root cause
the system
is
to blow up.
It's the piecewise linear approximation in the Euler integrator. So it's okay, not a numerical precision round off kind of thing. It's it's due to the approximations you're making in the discretization. So like when you fit a straight line segment along, so like the cartoon is if I draw the sinusoid and then I like take a point on it and fit a straight line, when the sinusoid curves, I'm overshooting, right? Because I'm not getting any of the curvature in my approximation. And so because of that overshoot, it always overshoots basically. And so as I do that over and over again, I'm going to basically just blow up because of the consistent overshoot of the linear approximation. But previously we were talking about the instability of the system. So we proved the integration is not stable. So what I showed specifically, right, is that the original continuous dynamics are marginally stable. But then if I discretize with Euler, the discrete time approximation using Euler is unstable. So the discretization made it unstable, right?
Okay.
In a way that's not physical, that is not true of the continuous system. So the message is the integrator is doing weird stuff to you. And the discrete time model that you got from that integrator is sort of not to be trusted. And you have to be careful when discretizing. That's the idea. It's that the stability properties of the original system are different from what you got from the discretization. Okay.
Okay, that's pretty clear. Thank you. Yeah.
Cool, cool, cool. So what I'm going to do now is we're going to do the exact same thing with RK4. So here's the RK4 that I just wrote down in the notes. Here's like, yeah, just time stepping it. And what I'm going to do now is same deal, same initial conditions, 0.1. And we're going to try, 10 seconds, 0.1 second time steps, just like we originally tried with the Euler. And as you can see, this looks pretty good, right? Like it's not growing, it's not shrinking, it's doing what it's supposed to do. So that's nice. Let's try some other stuff. So what I'm going to do now is, here's some fancier Julia usage. So what's going on here, this is automatic differentiation for diff, which I think probably most people have used if you do any like machine learning stuff. So I'm just forward diffing through the RK step with this guy to get the Jacobian, the discrete Jacobian that I need, because I don't want to write this by hand. And look at the eigenvalues. They're basically right on the money on 1 out to like 5, 6 decimal places. So like that's about as good as you can hope for, right? With something like this. So pretty good. They're just inside the unit circle. So these are stable. And they match what the continuous time dynamics should say to like 5, 6 decimal places. So pretty nice. Okay, so now
if you had a coarser time step, this would blow up too. Is that what you're saying?
Yeah. So here's the next plot. That's exactly what. So what I'm going to do in the next plot is exactly what I did with Euler. I'm going to plot these eigenvalues versus the time step length. So here I'm plotting this between 0 and 1. So time step varying from 0, like limited 0 to like up to 1 second time steps, right? So huge, huge age. So let's look what this does. So check it out. So like for small time steps, I basically right on the money, right on 1, which is what we just saw for 0.1 seconds, right? I'm over here. But as I grow the time step, I start to get weird stuff. So for some values here, basically it starts to go down under 1. So for some values of h, I get damping, artificial damping. So I'm going to dissipate energy artificially. And then there's this cutoff point and it starts to blow up. And now I'm adding energy and getting artificial energy increase and blow up. So I don't know, it's kind of fun, kind of interesting. The message is be careful with your discretizations and you can very easily get unphysical behavior. You should always check the stuff. So let's actually just visualize this real quick, right? So like if I go and change this, so for small values, it's super nice, right? So I do 100 Hertz, beautiful. Now let's make it big. Let's try to get into this damped territory. So like if I put in like 0.4, I should start to see artificial damping sort of behavior. It's also going to be really coarse, but yeah, so at 0.4 seconds, you can see it's damped artificially, right? It's starting to go down. I should mention to you, this is not related, like it's super coarse here, right? So you can see it's like really gross looking, but keep in mind, like I'm only plotting the XK knot points. The integrator is actually doing cubic interpolation between all these. So if I actually plot what's inside the integrator, it's still like cubically, it still looks pretty good, right? It's still pretty smooth. And you're getting this damping effect, right? So this is not a Nyquist thing. It's still sampling like dense enough to like easily reconstruct the function in terms of like frequency content. It's like a weird integrator time step phenomenon. Okay, any questions about this stuff?
I'm sorry, could you repeat what you did in that last plot?
Yeah, this last plot is the same one I did before. So what I'm doing is I'm computing these eigenvalues of the discrete time.
I'm sorry, the one before this.
This one?
This one, yeah.
Gotcha. Yeah, so I just changed the time step. So the original thing I did was 0.1 seconds h. So the time steps that I'm taking in the integrator, the times between my xk's. And so I varied this. So like this is 0.1 seconds between like the length of the steps I'm taking with the simulator, right? So what I did here in this plot is I varied that time step from like super tiny up to a full second. So I'm taking 1 second steps. And I plot the sort of the modulus of these eigenvalues. And for the real system, it should be 1, exactly 1, right? So we see this guy, it's pretty good. It's like pretty flat, right on 1 for like small time steps, like 10 Hertz, no problem. 5 Hertz, no problem. As I start to stretch it out though, they start to drop below 1, which means I'm getting artificial damping. So that the simulation is damped and is sucking energy out. when the real system, the real physics are undamped and like should oscillate forever at uniform amplitude. So what I did was I just went over here. I said, okay, yeah, like it starts to look damped, like 0.4 seconds is probably, you know, where we'll start to see some of that damping. So I went back up to my simulation up here, and I'm just simulating for 10 seconds. I put in 0.4 seconds as the time step and run this again at 0.4 seconds instead of 0.1 seconds. And now you can clearly see the energy dissipation, right? It's damping out. If I ran this longer, if I ran this out to like 100 seconds, you see it basically damps to zero, right? So like this system, it's getting the energy sucked out of it, and it's going to like go to nothing after 100 seconds. So like, you know, which is totally unphysical. This is not what the system should be doing, right? So if I went and put this back out to like the 0.1 seconds or 0.01 seconds, if I take 100 Hertz time steps, uniform amplitude, right? That's what it should do physically. We know from like intuitive, you know, energy conservation, basic physics, 0.1 seconds, pretty good, uniform amplitude, right? No problem. And now that there's this kind of threshold when I go to like the bigger values, now it's damped, right? And it should not be damped.
Yeah, makes sense. When you had like a very small total time, the blob was a little jagged. Does that have to do with?
That's just because the sampling is coarse, right?
Okay.
Like it's,
Yeah, sure.
I'm not doing fancy interpolation. Like strictly speaking, with this integrator, the integrator is doing cubic interpolation. I'm only doing linear in my plot because I'm just giving it the XKs and letting PyPlot like do linear interpolation for me. So it looks super jagged just because of the coarseness of the discretization. But what I was saying before is it's not like, it's still got enough samples in there for like Nyquist and whatever. Like it still accurately should be able to do this. It's only, yeah, it's this weird integrators are doing weird stuff to you kind of effect, right?
Okay, great. Thank you.
All right, cool.
Professor, quick question.
Yeah.
The plot you had below with the eigenvalues, does that reveal any sort of physical attributes of the pendulum? Because seeing a plot like that reminds me of like something out of like feedback controls or a small simple system responding to an impulse.
Yeah, I'm sure there is some relationship there. This is sort of related to like Z transforms and stability of discrete time systems with like, I mean, that's basically what this is, right? I'm basically plotting like the sort of eigenvalue things associated with the Z transform. It's not like strictly any of those things, I guess. I'm just like trying to get some intuition into what's going on with these things and just show you that there's demons lurking in there that you got to be careful with them. But yeah, like there's almost certainly some relationship you can pull out with like sort of discrete time, you know, sampled control systems and like those Z transform ideas. Yeah, off the top of my head, I don't have like a good hook to tell you.
It's probably related to the period, the epoch of this pendulum. Like if we change the length from 0.1 to 1 and its time period increases, we would probably be able to simulate with the largest time step without running into this.
Yeah, so what that would do is stretch this plot out, right? But the fundamental like sort of effect still exists. So yeah, you're absolutely right. There's sort of this interplay between the dynamics and the frequency content and the dynamics and the integration method and the interpolant that the integrator is using and the time step. Like these things are all coupled and all related. So like exactly what you said, if I stretch the pendulum out, make the natural frequency lower, the dynamics are slower, right? So I should be able to stretch the time steps of the integrator out. You would get this exact same curve, but it would be stretched in the time axis basically, right?
Gotcha, thank you.
Yeah, cool. All right, so let me switch back.
Yeah, on the same plot, I have a question. I have a request. Can you try out when you eyeball the plot when it recovers from damping?
Oh yeah, like over here?
Yeah, can you try that?
Yeah, let's try that. That's a good idea. I don't know. What do you think this is? 8.5? 9?
9.9.
Let's try it. I mean, it's going to be super coarse is the problem. But yeah, it sort of starts to look like, you know, it's not, we can run it for a long time and see what happens. So that's still damped. So maybe I didn't go far enough. So like if I go to like 9.5, yeah. But yeah, we're like way undersampling now, right? So now we are going to run into like Nyquist issues. So yeah, somewhere in there, there's a region where it's sort of magically, but that's also probably like weird aliasing effects and like undersampling effects too. So there's a bunch of weird stuff in there. So I would be, you know, take that with grains of salt. But yeah, so 9, it's still under damped, like 8.5. Yeah, that's really weird. It's going to do weird stuff because we're taking way too big steps, I think. But yeah.
You said for Euler, every time step blows up?
For this particular system. Yeah, and more generally for undamped systems that are supposed to conserve energy, Euler will pretty much always blow up. Euler has this like energy increasing behavior to it that's kind of always there. So if you have something that, yeah, sorry, go ahead.
I mean, there are some lines where it undershoots if you just do like Euler interpolation. So like if you match the frequency or something, could you not blow up or something like
maybe, but it's like it'd be a weird corner case. So okay, if you want to try this out, let me definitely go for it and tell me what you find.
Yeah,
you
just
can
curious.
Probably do it for like some weird edge case. You could probably engineer a situation where the combination of like aliasing weirdness and stuff would like perfectly cancel each other out. It's probably possible. I don't know. But yeah, if you want to go look into that, like please be my guest. It might be interesting.
Cool.
Okay, cool. So let's switch back.
Professor, I had a question. So, am I audible?
Yeah.
Yeah. So the minima of that eigenvalue versus edge plot, is there some significance to that edge?
Not that I know of. Okay. But maybe. Yeah, I don't know. I don't have anything good on cue for that, so I'm not sure. There might be. But yeah, again, like these things are complicated, right? These are all like weird nonlinear things. So like that curve is dependent on the exact system. So if you did a different system with different dynamics, it would look totally different, right? It depends on all these details. So there's like the only thing that I think you can really generalize from this sort of line of reasoning that I'm trying to show you guys is that like you have to always be careful with this stuff and you have to always kind of like watch out for these things. So like whenever you try to simulate something in discrete time, basically never use forward Euler. There's always a better option. RK4 is kind of the standard thing that everybody uses all the time because it's pretty good. It's like a good compromise between, compute and accuracy and stuff like that, but it still has the same demons lurking. And you have to like kind of keep an eye out for all these things. Okay, cool. So
a quick question. Is there any way to use the sampling resolution beyond heuristics?
So for simple stuff, yeah, it's really like at the end of the day, there's like Nyquist sort of limits associated with this stuff. So like you have to sample fast enough to capture the highest frequency in the dynamic, in the trajectory, right? That's sort of at the end of the day where the real limits come in. Yeah. All right, so my share just crapped out apparently. So let's get back to this. Let's see how we do on time. All right, yeah, we gotta hustle a little bit to finish up here. So, okay, so takeaway messages from this part of the discussion. So first off, for RK4, basically like the accuracy win is like far outweighs the additional compute cost of versus like forward Euler. This is borne out in practice. Like you could try a whole bunch of experiments yourself if you care. It's like pretty much always a win. So like, do it basically. What else? So yeah, like, and then the other thing here is based on what I just showed you, right, is that even sophisticated integrators, even like high order fancy stuff, has these demons lurking under the hood. So no matter what you do, like you always kind of have to have this stuff in the back of your mind. You still want to sanity check your results against like conservative things, dissipative things, make sure energy does what you expect, that kind of stuff. And what is going on? I'm like writing sideways on my desk because my stuff is freaking out. All right. And yeah, just in terms of bigger picture, the reason we're doing this stuff is like these things happen very easily when you start doing trajectory optimization kind of things. You always have to like really think hard about if what you're doing makes sense when you get these answers out. All right, cool. So that's explicit integrators. We're going to talk real quick about implicit methods. So implicit, say, form of these discrete time dynamics. Let's call this, I guess it should be clear, so I'll use a little d for this guy too. So these are called implicit because the xk plus 1 is buried inside the nonlinear f. And so we have to like work a little harder to solve these things, at least in a forward simulation context. So simplest example, is the following thing. So this looks like Euler, but I'm evaluating the f at the future time step. So this is called backward Euler instead of forward Euler. So yeah, that's weird. So that's sort of weird. How do we do that? So in general, right, so f is our nonlinear dynamics. The x is buried in there. So this whole thing is nonlinear in the future time step. So when we simulate this thing, we basically end up having to solve a root finding problem to time step the system. So I can rearrange that equation, right, that I just wrote as in the form I showed before, right? And this will look like xk plus. So I write it like this, and then I solve a root finding problem in xk plus 1. And like generally, you'll start with a guess of, so you start with a guess value like xk plus 1 equals xk. It's usually a safe bet and almost always works. And then you just solve this for xk plus 1. So we'll talk more about the solving the root finding thing next week as we get into optimization. And real quick now, I want to switch over back. This is super annoying. I need to find a better way to do this. Stop share, share again.
Yeah, quick suggestion for these. If you don't like to switch between them, you may try to stream your past screen to your computer and then.
Yeah, I tried to get that set up before this and it didn't work. So I need to try again.
Yeah.
Okay, so here's the backward Euler now. Same stuff as before. There's some weird details in here about the like backward implicit part that I'm not going to talk about yet. But don't worry about that. Basically, it's in here. Trust me. So backward Euler, we're now going to plot the pendulum. Same deal. 0.1 second time steps, 10 seconds. What's going to happen? Look at that. Now it's damped. And I can stretch this out. Let's do 100 Hertz instead of 10 Hertz. 100 Hertz, still damped. So backward Euler has exactly the opposite energy behavior from forward Euler. Instead of adding energy, it's artificially damping the system. So that's it. So any questions about that? Does anyone want to try plugging in different weird stuff in here? Cool. All right. So
how to calculate the Jacobian for this way?
Yeah, so this is gonna be in the first homework, so I'm not gonna tell you. You will do it next week.
Okay.
Yeah, like if you, so yeah, it's gonna be on the homework, like some of the stuff. So like I'm gonna tease it now, but then you'll have to do it. So like if you have questions about it next week, we can talk about it in office hours. Okay, okay, pendulum simulation.
So I have a question about what the ideal integrator then is sort of just at the boundary of the unit cycle, right?
Yeah, and also a perfect integrator would produce the exact behavior of the real system, right? Reproduce the ODE exactly.
I guess what's kind of counterintuitive to me is the idea that when you have a more stable system way within the unit cycle, it's not actually ideal for integrating your system.
No, not really. Like so even if you have a stable system with damping, this is going to add more damping. So it's going to give you an answer that doesn't blow up, but it'll still be wrong, right?
Yeah.
So the ideal thing will like exactly behave like the real system, and that doesn't exist. But there are definitely methods that are closer to that than these things, right? That are super common. Okay, so I just wanted to. So this thing has opposite energy behavior, and actually that little plot about the overshoot on the sinusoid. If you do backward Euler, what you're doing is you're evaluating the slope at the future step. So you'll notice exactly the same thing before, but it undershoots always instead of overshoots. So like you can kind of intuitively get the cartoon picture there from that. Okay, what else do we say? Okay, so comments on this. It added artificial damping. This is unphysical and nominally bad if we care about physical accuracy, but yeah, like whoever, I don't know who was just talking to me, sorry. Yeah, like this is unphysical, but it's sort of in some sense, if all I care about is getting a simulator to run and not look stupid and like not explode on me, then this is maybe somewhat desirable to have this sort of artificial damping. It sort of makes things more stable in some sense, right? So, so while this is unphysical, it lets us take bigger time steps in the simulator without things blowing up, and it's sort of convenient. So because of that convenience, these backward Euler methods are actually very common in low fidelity simulators used in like computer graphics, a lot of game engine type stuff, and in some robotic simulators. They're also widely used in a lot of simulators. So a lot of simulators use these methods because they basically let you get away with things. When you take big steps, they let you get away with running the simulator fast with large time steps because of this artificial damping. So you'll probably see these in your life in various places because of that.
Cool.
Is there a way to somehow like take an average of the forward and backward Euler to like so that they cancel out each other's energies?
Yeah, there it is. There's stuff like this. Yeah. So there's some other stuff that's gonna be on the homework yet again.
Okay.
So yeah, stay tuned for it'll be out next week.
I had a question.
Yeah.
I've heard this term stiffness.
Yeah.
I don't know what it is though.
Yeah.
So the question is like, what is it?
It's actually very ill-defined. You'll find like there aren't really good, consistent, hard mathematical definitions. It generically refers to systems that are hard to simulate. And where it's actually coming from is specifically like stiffness in the sense of a stiff spring. So if you try to simulate like a spring damper system with a really large stiffness, even if it's like super damped, right? So you can have like an ideally perfectly damped but really stiff linear system. If I give that like a big impulse and then try to simulate it with these methods, because of the stiff spring, there's like high natural frequencies associated with the system. So I end up having to take really, really small time steps in these integrators to make the simulation not blow up. So yeah, that's what it's referring to. That's where it comes from. But it's also applied to like all kinds of nonlinear things that don't have stiff springs in them that are just generically hard to simulate. It generally means it's a system where you have to take really tiny time steps.
So is it like a property of the ODE? Or...
Yes. Yeah, yeah, exactly. It's a property of the original ODE, of the original physics of the system. Yeah. Yeah, there's lots of examples of these things. But yeah, you'll find in the engineering community, it just generically means hard to simulate. Cool.
Isaac, I think our RK4 is evaluating the dynamics at the different points between H. So theoretically, like if we evaluate dynamics at multiple points, like 100 times, evenly distributed on this time interval, you can get an arbitrary, like larger precision.
You can, so, yeah, this is absolutely true. Yes.
Yeah, and it uses.
It's like, just not necessarily a win, it turns out. So what you're talking about are like sometimes called collocation methods or pseudospectral methods. It basically comes down to like RK4 is fitting a cubic. So you need 4 points to fit a cubic. You can play that game as far out as you want. So you can start taking more and more samples and fit higher and higher order polynomials. It just turns out that it's not always really advantageous because the real dynamics are not always that smooth. So that only works, right, if the system's like smoothness up to that order, right? So for the cubic, it only really buys you a win if the real dynamics are like C3 smooth or whatever, right? So if they're not, then the cubic is not a good fit. And so it doesn't win. And so if you go to higher order polynomials, you need more and more smoothness out of the real dynamics in order for it to actually be advantageous. And it's often not the case that that's true.
Got it.
Okay. Cool. Okay, so last thing to talk about. Oh yeah, so like some takeaway stuff on that stuff. Okay, so generically speaking, implicit integrators are typically like more stable than their explicit counterparts. So there's like, for just about every order of integrator you can come up with, there's like an explicit and implicit version. You can come up with different versions of these things. The implicit ones, they're usually more expensive to forward sim because you have to do this root finding business, but they're often more stable and so better in certain respects, right? So yeah, like for forward sim, we have to solve this implicit equation, which can be more expensive. So that's kind of annoying. But sometimes it is worth it. And in particular, like really gnarly stiff things, implicit's better. So like the stiff stuff happens a lot in, for example, finite element methods where you're trying to simulate like floppy, flexible things. Those are often very stiff equations, and implicit methods are standard in those fields because of that. And then the other caveat though is, okay, so these things you have to solve this root finding problem. That's annoying if you just care about forward rollouts. But in a lot of direct trajectory optimization methods, we're not doing forward rollouts. We're applying these things as constraints. And there it's basically free. It doesn't actually imply any computational extra cost. So they're widely used in direct trajectory optimization methods, which is why we're talking about them. Cool. So yeah, so they can be a big win for direct trajectory optimization. So in fact, the classic direct collocation method that probably a lot of you have heard of uses an implicit third order integrator. for this reason. Okay, cool. Last thing, real quick. Hopefully we can get, yeah, we'll be cool on time. So the last thing I want to talk about is, so all the stuff we talked about so far has been about discretizing the states, the state trajectory, like x of t. We're going to talk really quick about discretizing the controls. And this is like a much simpler or shorter topic than the state stuff. Largely, I think, because we get to pick it. Okay, so first, simplest option is the following thing. It's sample and hold, aka zero order hold. You just set u of t equal to uk over the whole time step. And okay, this is called zero order hold. And it looks like this if I plot it. Super, super kind of intuitive. Look at that, snaps to a straight line for me. Amazing. So you get stuff like this, right? So I'm going to sample it at this time step, integrate, and keep it, and then same thing over here, right? So it's like piecewise constant type of deal. This kind of thing. Okay. So this is really easy to implement. So that's sort of one reason it's good. But if my trajectory is smooth, i.e. if I have like some continuous u of t, then this is a pretty bad fit to a continuous u of t, and therefore it can take lots and lots of knot points, lots of sample points in order to like accurately reproduce some continuous u of t. So that's not great. And the lingo here, knot point, is like control trajectory optimization lingo for sample point. Also, it's a common lingo thing. So sorry if I slip into that without telling you what it is. Okay, next option. So zero to hold, easy, simple. Possibly better option, not necessarily for sure, depends on the situation, is the following thing. So it's so this is sort of maybe annoying. This is a piecewise linear interpolation called a first order hold.
What is that denominator there? Is that?
Oh, that's an H, as in the time step.
Okay.
Yeah. Cool. So yeah, if I can do the cartoon plot on this thing, if I have, a bunch of samples sort of like this, it's, pretty obvious what's going on. It's going to do this kind of thing, right? That's it. So there you go, something like that. So this is potentially better if you have a continuous control signal, right? If I have a continuous U of t, this is a better approximation than the zero order hold. And so for things that are kind of continuous or smooth, you can probably get away with far fewer knot points with this kind of setup, which means smaller problem sizes, faster solve times, all the good stuff, right?
Can you explain, is t actual time here? Why is h? H is delta t, right?
That's right, yep. Yeah, so what I'm doing there is I'm just getting the slope over the interval, right? UK plus 1 minus UK over dt. So that's the slope. And then I'm just like multiplying that by the time into the step, which is t minus tk, right?
Okay.
So it's just affine, right? It's like the UK, the initial value at the beginning of the step, and then like the slope times the time over the step, right? That's all that is. It's like really simple. It's just sort of like probably hidden in too much notation. Okay, continuous U. Yeah, so if U is continuous, this is a win. You want to do this probably if your control signals are like smooth or continuous at least, right? And it's also extremely cheap to implement. So like it's basically not, it's almost zero extra work over the zero order hold in terms of like problem size, complexity, solve time, et cetera. It's almost not any extra work. So it's definitely, if you know the things are kind of continuous or smooth, definitely do it. It's worth it.
So in practice, basically the issue of discretization is limited by, say, your ADC, right? So ADCs are zero order holding in general. Is that true?
Yes, but we're talking about stuff that like all the stuff we're talking about lives like many layers above the ADC in your practical system. Like these controllers we're talking about here, if we were to do like MPC on something, these typically run at like tens of hertz up to hundreds of hertz on practical robotic systems. And then like your low level stuff on the motors, right? Your motor drivers are probably running at kilohertz and your ADCs are running like kilohertz, right? So this is all like sort of abstracted a couple layers from that stuff, from those hardware details, I would say.
Okay, but in terms of the discretization of what is possible to control, you're still limited by what the hardware can produce, right?
Sure. What I'm saying here though is like, what this might let me do is this might let me take 10 hertz time steps in my trajectory solver instead of 100 hertz steps in my trajectory solver, which means my problem size is 1/10 as big, which means I can solve it way faster online. So this might be the difference between a real-time algorithm and like something that's not fast enough to run real time, right? And then like what I would do in practice is if I got this answer out that looks like this, I can interpolate into it at a kilohertz to feed into my ADC if I want to, right? So what I'm saying is that this is going to happen like way lower frequency than like the ADC stuff you're talking about.
Okay.
Pretty much always. Cool. All right, so that's cool. Yeah, and then the last thing, right, that I want to say about this is like, this is super common in practice. This first order hold thing is in the benchmark standard direct collocation method. This is like classic. So yay, it works, it's good. And we're going to talk about this stuff. So then the last thing I wanted to like briefly touch on is like, we kind of already hinted at this with Shuo's comment. You can keep playing this game forever, right? Like I can keep like adding in higher order polynomial interpolants and stuff. But, and there are methods that do that. There are methods that were like super popular and like made lots of noise in the like late 90s, early 2000s that basically used like ultra high order polynomials called pseudospectral methods. Turns out practically they're not that useful. They don't actually do better. And the reason is that the control signals are very frequently in our problems non-smooth. So like if anyone's studied control at all, you probably heard of bang bang control, right? Things like this. So like, especially when you have constraints on the system, like torque limits, it's really, really common to get control commands out that like saturate the actuators and go right up to the torque limits and bounce around like that. And those kind of signals that go right up to the torque limits and saturate, et cetera. So even if the system dynamics are smooth, if you're going up to your torque limits and saturating, the control signals are not smooth. So as a result, these higher order, like smooth polynomial interpolations on the control signal are totally useless and don't buy you anything practically because they're just bad approximants for these non-smooth sort of jerky control signals. So that's kind of the last thing I wanted to mention. Yeah, I will write that down. But yeah, we're basically out of time. So if anyone's got to take off, go ahead. I'm just going to jot that down. If anyone has any questions while I do that, shoot.
I guess, can you give like while you're writing, if you can do both
Yeah.
of them, U is like maybe like an output, maybe it's like a torque or like a voltage to the motors. Can you give some like more physical intuition for what U is here again?
Yeah, U is the control command. So yeah, in general, like it can be anything, but practically it's usually motor torques or thrusts or throttle commands on a car, right? It can be like, it depends on how you set up your model and what exactly you choose to model. And there's like often varying levels of fidelity here. So like, you know, you could, for example, if you're using like a straight physics model for like a quad rotor, say, you might throw in the thrusts for the propellers, right? You might just do it in terms of thrust, and then the U's would be thrust, and then you'd have some lower level like motor controller that's taking that thrust value and translating that into a motor voltage. That's pretty common to have like some hierarchical kind of setup where this stuff is doing like the physics stuff, and then like there's some low level thing taking care of like the details of the motors and stuff like that. But yeah, you could also write a more high fidelity model that bakes in like details of the motor dynamics and weird, you know, effects of like the fluid in the prop. And then you would use those motor voltages directly in your model as the U's. And you could do that too. Although that's sort of less common, I would say. So yeah, like it can be kind of anything, but generally speaking, like I'd say most common thing is for these to be like the physical quantities of like torques, thrusts, that kind of stuff. But yeah, there's no reason it can't be sort of more in the weeds stuff. Okay, so yeah, I'm just looking at the questions here. I'm just finally getting some of these, sorry. So one of the questions was, does RK4 run in the back end of ODE solvers in Python and MATLAB? Yes, with more complicated wrapper magic. So ODE45 in MATLAB is, as someone pointed out, it's RK4 plus a fifth order interpolant, and they run them both in parallel. And then they do adaptive step size error control. So they basically like run the fourth order and the fifth order step simultaneously, compare them. If they don't match well, it implies that your step size is too big, and then you shrink the step size. So they use that. That's a really common trick with Runge-Kutta methods. You run two at different orders and try to enforce them matching, and you run like an adaptation kind of loop on that. So that's what our ODE45 does. Yeah.
So is that like the state of the art currently?
It depends what you mean by state of the art, right? So like this is a broad field, and there's like lots and lots of methods, and lots of state of the art in one area is different from the other, right? So like in like finite element and CFD land, the state of the art stuff are like are implicit methods. Okay. And then if you go to like astrodynamics, which is a field I like used to play around in, which is like spacecraft stuff, like trajectories to get to Mars. The state of the art there are very high order Runge-Kutta methods, variable step Runge-Kutta methods like like RK78, or even higher. Like people use even up to like 14th, 15th order Runge-Kutta methods, because those trajectories are very smooth and they're really long, like months to get to Mars. So it helps there. The high order polynomials do work because they're so smooth and so long. And that lets you take really big steps, which is advantageous, right? So it depends on the problem, really. Those astrodynamics problems are not stiff. They're very like benign and smooth. So like high order explicit Runge-Kutta works well. Whereas in FEA, they're like really fast dynamics, both fast and slow, all in the same ODE, really large, and like low order implicit methods are what you want there, right? So like it's sort of all over the place.
Got it, thanks.
But yeah, for like benign first thing you should try kind of stuff, like in your own work, like Runge-Kutta, mid fidelity Runge-Kutta is like the way to go. So like RK4 or something like ODE45 that's got the adaptive stepping are like the standard sort of things that'll get you like reasonable answers most of the time, unless you're trying to do something harder. Yeah, Brian suggested the Julia ODE package. That package is beautiful. It's probably the best ODE package on Earth ever. So that's definitely worth a look. Oh yeah, if anyone has anything else, definitely like hit me up. I'll hang out for like a few minutes here.
I had a question.
Yeah.
So going back to like the first order hold thing, right? That is that same sort of issue as like the backward Euler, right? Where you have to know the thing ahead of time.
Yeah, sort of, but not. It turns out it's not the same flavor of problem here. So this is in the context of trajectory optimization now, where we're trying to solve for the U. instead of just running a forward simulation. So like if I'm doing TrajOpt, I'm saying, yeah, I'm looking ahead into the future, or I'm doing this offline. I'm saying like, okay, here's my robot. Here's like initial state, goal state. I want to know what to do. Here's my trajectory of like 100 time steps. Here's my 100 U's optimized. Tell me what the right U's are. So in that context, I'm looking at the whole trajectory all at once in one big optimization problem, and they're all decision variables. And so in that context, like this sort of like non-causality business doesn't really show up and isn't really a problem.
Okay. Yeah, makes sense.
That makes sense. Yeah. So that issue, that like non-causal kind of thing, is only an issue with these. And for that same reason, by the way, the implicit integrators are also no big deal in a trajectory optimization context for exactly the same reason. They only incur this weird extra cost of like having to do a root find on this like non-causal equation if you're just doing a forward rollout, if you're doing forward simulation. So that's the only time they're like actually problematic and like have some extra work associated with them. Otherwise, they're totally fine for a lot of the stuff we do.
Okay, yeah, makes sense.
Will you share the Jupyter notebooks you used today?
Yeah, absolutely. Okay. That's all going up with the notes right after. As soon as I get a chance to PDF everything. Yeah.
Exactly. If a system is not smooth to the fourth order, can you sometimes use like RK3 per se?
Yeah.
Okay. So like, is there a way? Can you maybe
RK3 exists? Okay. RK3 is in the same original classic paper that RK4 is derived in. So they both exist. It's just that RK4 is, for whatever reason, become the de facto standard, like what everyone uses. So yeah, sorry, what else were you gonna say?
I was just gonna ask, like, I'm guessing you can kind of analyze the system and get an idea of what order or what RK n would be best, and then kind of apply whatever is best to that specific system.
Yeah, I would say like probably that effort is like not worth it in a lot of cases. Like probably the right move there is to use, like, if you're worried about that kind of thing, like the standard toolboxes. So this is worth worrying about maybe if you are doing some like real-time thing, like what we're talking about doing with a control problem, where we like absolutely need to dial it in and need it to be super fast and super optimized for some real-time application, then yeah, you might want to do this and go through this effort. But if you're just like sitting there offline and like care about simulating some stuff to see what's going to happen, the thing I would do is just use one of these standard off-the-shelf Runge-Kutta solvers that do variable step, like adaptive step. Because what those will do is you basically tell them an error tolerance, and they'll like run 2 Runge-Kutta steps in parallel and like adapt the step size to make sure they hit the error tolerance you asked for. And those, for like non-stiff systems, they just work, and you don't have to worry about it, and like they're kind of magical. They do break down on like hard problems, so like there's stuff they won't work for, but if you're just trying to like, you know, casually simulate stuff, those are like kind of the thing to do, I would say.
Okay, thanks.
Professor?
Yep.
For like the generating the continuous time controls from like a discrete number of points.
Yeah.
It seems like, because the trajectory, at least for like the first order hold, seems very, you basically have like discontinuities at every point, right?
They're not discontinuities. It's continuous, right?
Like
so that trajectory is C0, right? Yeah, you're right. It's non-differentiable at those points. Yeah, in time. Yeah, that's exactly right.
Mm-hmm. So do people like, because when I look at it, the first thing I thought was like maybe like polynomial fitting. Is there like a reason to maybe do something with that instead, or?
Yeah. So that's exactly what I'm like writing maybe down and was trying to talk about there. So yes, you can do that. People absolutely do it. And in fact, in like certain applications, like I mentioned, the aerospace stuff where you're doing spacecraft trajectories to like Mars or whatever, in those applications, the trajectories are very smooth, the dynamics are very smooth, and high order polynomials do work well. So in that context, yes, people absolutely do what you're talking about. They'll use high order splines. They'll use like 7th to 8th order polynomials and all that good stuff. And it works there. For a lot of robotics applications though, the dynamics are not that smooth. And as a result, the higher order polynomials don't buy you anything. And in fact, you get like Runge phenomena, this like overshoot ringing craziness. where you try to like approximate, you know, like a non-smooth jump with a polynomial, you get like artifacts and all kinds of weird stuff. So it's like, it's actually not a good idea to do it on a non-smooth function, right? So if U of t is really, really smooth, then yeah, it's a win to use the higher order polynomial. If U of t is like jumpy, jerky, you know, kind of thing, then it's not a win. And in a lot of practical control settings, that's the case. Like it just happens that like, even just because of torque limits, like just when you have torque limits on your motors and you like hit the limits, that's going to induce like, you know, sort of like this kind of jerky stuff where you're saturating and then saturating the other way. And you get, this is like so-called bang bang control. And that comes out a lot. And in those cases, like the smooth polynomial representation is not good. It just doesn't, it doesn't buy you anything, right? And in fact, it can be worse than the like zero first order hold stuff.
If you were to use maybe like for example, like a PID, like a well-tuned PID would, I guess it kind of, I guess PID kind of does simulate like a second order.
Well, if you write it down in continuous time, like it's a continuous function, right? What this sort of is all applicable to is like when you discretize that and do it in a computer, right? So like that's, this whole discussion is all about like when I'm doing things in discrete time on a computer, like this is what you get, right? So the PID stuff, yeah, like you have to discretize it, right? At some point, if you want to implement it on a computer. So then some of this stuff would show up. The stuff we're talking about here is like more applicable to like trajectory optimization kind of stuff, which is what we're mostly going to talk about in here, and MPC and that kind of stuff. Less so the classical like PID stuff, but yeah, like it's relevant whenever you're trying to discretize stuff in time. Yeah, that's kind of what I was trying to get at today.
Okay, got it. Thank you.
Yeah.
Hey, Zach. So for RK4, when we're simulating forward, we kind of like for the states, we look ahead in time, like for several like points. Like what about for the control signal? Do we do the same thing here, but using this first order hold function?
Yeah, so like if you wanted to do RK4 step, let me go back to that. So where did I write it down? Here we go. So RK4, here's one RK4 step, right? If I do this with controls, if I do it with the zero order hold, I would just plug in the same UK for all of them, right? So I would have like, you know, UK, blah, blah, blah. If I did the first order hold with the linear interpolation, this would be UK. Then here it's the midpoint, right? So I'd have UK plus the average basically, right? Like UK plus 1 minus UK over, or I guess it would be like an average. Yeah, so this would be an easier way to write that down is UK plus 1 plus UK over 2. So this would be for this guy, and then the last step would get UK plus 1.
I see. Okay.
So that's exactly like if in RK4 how I would implement the first order hold. And then zero order hold's obvious. You just always plug in UK.
Okay, got it. Thank you.
Yeah.
I had a question. You had mentioned the bang bang control as a kind of an example of that discontinuous signal. If your control signal is a PWM duty cycle that is essentially just setting the frequency of that on, off, saturate, and close, is that still considered continuous in that case, or would it matter the kind of the end effect of what you're controlling?
Yeah, I would say like, so that PWM stuff is happening at really high frequencies, right? Like much higher than the relevant system dynamics. So like, I would probably not try to make that, you know. So the idea with this stuff is like, what we're trying to do here at the end of the day is come up with the smallest, you know, like representation of the trajectories of the dynamics possible, like the most computationally expedient representation we can, because we want to solve this stuff fast typically. So yeah, like usually you're going to formulate this in the way that's the cheapest to numerically solve. So like there, yeah, like if you have, like, I would probably not put the details of like that PWM stuff in here, right? Instead would just have it be like the average value that the PWM thing is trying to like achieve, right? Would be what I'd stick in here probably. And so like then the saturating thing would be like, you know, where the PWM's on the whole interval, right? Versus like off the whole interval or whatever.
Okay, I see.
Like those extreme values, which yeah, I mean, it depends on the application. So like if your stuff's really smooth, then yeah, like first order hold works pretty good for that. You may be able to get a win. And when I say a win, what I mean specifically is if your signal is smooth, if U of T is smooth, then like going from 0 order hold to first order hold is a big win, i.e. you'll be able to use way fewer not points to capture the dynamics and like solve the problem. And then your problem size gets smaller and then you can do it faster online, right? So that's what I mean by win. So like if it's really smooth, first order hold's a win. You'll do better. You'll be able to solve faster. You can use a smaller formulation. If it's really smooth, then you can keep playing that game and probably keep winning, right? So like you could go from linear interpolation to quadratic spline interpolation. And maybe then if it's really nice and smooth, you can like, that's a win. And then you'll like keep going and like, you can use a smaller problem size, right? So that's kind of what I'm talking about. So like always in that process, there's some trade-off. Like if the control is really smooth, then high order polynomials work. Then maybe you can get away with fewer not points, smaller problem, go faster, et cetera. But yeah, often like it gets more complicated to implement and like there might be diminishing returns, right? It just depends on the problem.
Okay, thank you.
All right. All right.
Oh, sorry. Go ahead.
Oh, go ahead. Yeah, I'm done. So like, oh yeah, if anyone has extra stuff, I'll like hang out and whatever.
Yeah. Back to the analysis of the eigenvalue, a norm of eigenvalue of the Jacobian matrix. You're saying that it should be constant 1 with 0 input. So it seems you treat it like a energy changing rate of the system. But what's the connection between them?
So what I was trying to get at there is for the real system, like the pendulum that we were trying to simulate, the real behavior is perfectly conserves energy, undamped, right? And so the real dynamics should have, so the real dynamics in continuous time have zero real part eigenvalues. In discrete time, the real thing would correspond to having eigenvalues with exactly modulus 1, like right on the unit circle, right? Does that make sense?
Yeah. But what if you have non-zero input? So could you still get like a desired discretized eigenvalue, non-of eigenvalue?
So what we're talking about here is like just passive dynamics, just simulation. All I'm trying to tell you is that like this process of discretization of like approximating the continuous time dynamics ODEs in a computer with like some sort of discretization, some Runge-Kutta method, whatever you want to use, is always going to introduce some kind of artifacts and some kind of approximation, no matter what you try. And like this was, you know, it applies with controls as well, but it applies even without the controls, right? So I was just trying to show you the simplest kind of cases I could come up with. So no control, simple pendulum, right? Simplest like nonlinear system I can think of. And yeah, you see this behavior where the real physics should have exactly eigenvalue modulus exactly 1 in discrete time. And then when you put it through forward Euler, you get bigger than 1 and it blows up and it's unstable. You put it into backward Euler, you get smaller than 1 and it decays when it's not supposed to. You put it into RK4, it's pretty good. It's like out to like 5-6 decimal places. It's almost exactly 1, right? It's good to 5 decimal places, 6 decimal places. So that's really good. So that's sort of the idea behind that is, yeah, RK4 is really good. And it's going to get you pretty good answers that you can depend on most of the time. So that's why it's sort of like this workhorse algorithm. But even there, right, it's good to 5-6 decimal places, but it's a little off. So if you simulate that for a long time, you'll see the decay.
Yeah.
Right. So that's kind of all I'm trying to say is like, these things all do weird stuff when you discretize that's not physical, and you should know about it, and you should check, you know, sanity check, make sure you're sort of getting the behavior that you expect that you should get in the simulator.
Yeah, I see. Thank you.
Cool. Okay, anybody else have anything?
Yeah, actually I had a quick question.
Yeah.
I've been recently reading into a group of papers that are looking for nonlinear dynamic inversion for high performance control, where you're trying to restructure the system dynamics in order to make the problem a little bit easier. And this is used in flight systems where they're basically, they have really good modeling and good. They can throw lots of money at the problem effectively to solve that. Where we may not have that same opportunity in a robotic system like what we would deal with. So can you maybe give some of the trade-offs of doing system design for high performance control whenever you could be doing some sort of like nonlinear dynamic conversion versus what we might be considering with more like direct trajectory optimization and BC kind of thing?
Yeah, so this is like a really like, sort of interesting area. So like, all these kind of like dynamic inversion, dynamic cancellation kind of things, they are very common in robotics as well. They're sort of commonly called feedback linearization or partial feedback linearization. Have you heard of those things before?
Yes, we talked about it with Dr. Geyer before with the manipulators.
Okay, that's the same exact idea. Like what you're trying to do there is you have a model of the system. You're essentially using your controls to cancel out the natural dynamics and then like do whatever you want from there, right? So yeah, it goes by a lot of names and there's like subtle variations, but that like feedback linearization, partial feedback linearization, model inversion, whatever, like there's a bunch of names for it. That's kind of the core idea behind all of them is you try to cancel out the dynamics using your model and your control inputs, right? Is that where we're talking about?
Yeah, so I was just kind of curious. I mean, if you can do that and replace the dynamics with something simpler.
Or... Why wouldn't you? Yeah,
right.
Okay, cool. Yeah, we're on the same page. Okay, so the why wouldn't you is, number one, often you can't. In particular, if you're under actuated and you have fewer control inputs than you have, degrees of freedom, et cetera, you can't do it. So you can sometimes do partial cancellation, aka partial feedback linearization, but then you still have to deal with some of the nonlinear dynamics. You still need something else. So that's number one. Number two is performance. And there's a couple of flavors of this. So one is if you don't have a super accurate model, that dynamics cancellation business is quite dangerous and can lead to like weird effects that are sort of, there's demons there, right? So that sort of causes robustness problems. And then the other one is performance in the like absolute kind of like performance metric sense, in that what's going to happen when you cancel those dynamics out is like in your controller, you can't take advantage of them. So often these kind of, the classic example of this sort of cancellation, feedback linearization stuff in robotics is Asimo, the Honda humanoid. Are you familiar with this? You've seen the videos?
Yeah,
so it's the classic robot, right? In that it always walks in this like hunched sort of like looking pose, and it looks very robotic and very unnatural. And it turns out it's very, very energetically inefficient. And they do exactly this stuff. They do partial feedback linearization. They try to cancel out all the robot's natural dynamics, and then they just get it to try to track, some trajectory for the feed or whatever. The result is that the thing can only stay running for like 10 minutes on a battery charge. And if you look at its total cost of transport, like the energetics of its walking, they're horrendous and like way, way worse than what a human achieves. And in fact, what some other robots that don't use this kind of control can achieve. And the reason is, that dynamic cancellation stuff, you're doing that with your actuators, and that has an energetic cost, right? And what natural walking does instead is embrace the real nonlinear dynamics. It's like when we walk, we basically, like, we only use our muscles for like some parts of our leg swing, and we're relying on the passive like pendulum dynamics for the rest of the time. And so you can get away with like way less actuator effort if you actually think about, reason about, and leverage the natural dynamics of the system. So that's sort of the big reason. Energetic efficiency is like way better if you actually embrace the dynamics.
Right, and so I guess in the case that I was seeing, since it's a jet, then effectively you have about as much energy and you have as many actuators as you effectively want, right? So
yeah, so in that context, it maybe makes some sense, and these methods are like potentially can be like so for like certain aggressive flight regimes, this can work. But I'll tell you, yeah, from like personal experience, those the models for like very aggressive flight regimes, like high angle of attack, high side slip, are not good. And there's lots of demons in there. And there's lots of crazy things you can do at those high angle of attacks by taking advantage of the full dynamics that you can't cancel out. So like as far as AI, like jets are still underactuated, and the only context in which you would be fully actuated and be able to cancel everything out would be if you had like crazy thrust vectoring, right? That kind of thing. So yeah, like quad rotors are super aerobatic and stuff, they're underactuated, right? They only have 4 inputs for 6 DOF. So yeah, jets are the same way. Like if you have full set of control surfaces, you have thrust, pitch, roll, yaw. That's 4, that's not 6, right?
Great, thank you.
Yeah, cool. All right, we good? Anybody else? All right, gonna call it a night then, guys. Thanks everybody. Talk to you next time.